Okay, can everybody see my screen?
Yes, thank you.
Okay, so as mentioned, I will be presenting the paper Exploring Neural Network Training Dynamics through Binary Node Activations. This paper was co-authored by Prof. Marelie Davel. Deep neural networks are particularly useful as a tool for extracting complex relationships from a large amount of data. However, no theoretical framework with which to reason about the generalization ability of a DNN model exists. The importance of generalization has led many to study it. Some of the approaches to studying generalization consider the geometry of the loss landscape, where the intuition is that flatter minima lead to less output variation when the parameterization or input is varied. Statistical measures of stability and robustness are also studied. Others focus on the complexity of the hypothesis space, where generalization is expected to decrease with unnecessary complexity. Finally, the distance to the decision boundary is considered through margin distributions. These approaches focus more on the network as a whole and less on the individual components of the network. By considering individual nodes, the idea of a sample set emerges. The sample set of a node is the set of samples that activate the node. For this paper, we study networks with rectified linear activation functions, in which a node is considered active if its activation value is non-zero. Since our main focus is on the evolution of sample sets, it is helpful to think about sample sets as being identified during the forward pass through a network. During the backward pass, when weights are updated, the sample sets are refined. Although many interesting characteristics of sample sets had been presented in other work, the evolution of sample sets throughout training has not yet been studied. The main contributions of our paper are the following. We motivate the importance of sample sets as an analysis tool. We demonstrate that the evolution of sample sets throughout training is consistent across several networks. Lastly, we interpret our findings in terms of a high-dimensional clustering process. With a few assumptions, we can derive the conditions under which samples are added to or removed from a sample set. If we assume that the only weights that are updated are those leading into the node considered, a sample will be added to the node sample set or remain in the sample set if the following holds. The sample activations are shown in red in the equation and figure, and the weights to be updated are shown with a W in the equation and in black in the figure. The eta denotes the learning rate, and the summation is across all the samples in the node sample set. If this inequality does not hold, the sample will be removed from the set or remain outside the set. Essentially, the training process constructs a margin around the decision boundary, and any samples in this margin will be added to or removed from the sample set. The size of the margin is determined by the alignment of the sample activations with those of samples in the sample set, as shown by the dot product under the summation. The loss contributed by each sample in the sample set also influences the size of the margin through the node-supported cost. The node-supported cost is the derivative of the sample loss with respect to the node activation. If the loss is large, the margin will be large, and samples will be added to or removed from sample sets more easily. This image illustrates the idea of a margin in a low-dimensional space. The blue arrow represents the vector of weight to be updated, and blue and orange dots represent samples in the node sample set. Black and green dots represent samples outside of the node sample set. Any samples in the green area will be added to the sample set during the next update, and samples in the orange area will be removed. To study the evolution of sample sets throughout training, we trained several fully connected networks with the hyperparameters shown here. We trained all networks with both mean squared error loss and cross entropy loss using the Adam optimizer. All networks were trained on the MNIST dataset for 200 epochs. We defined the following quantities and measured them for our training. The activation fraction of a node is the fraction of all samples in the node sample set. The predictability of a node is, intuitively, the average amount of information known about the binary activation of the node, given the class of the input sample. Here, the binary activation of a node is 1 if the node is active and 0 if the node is not active. Finally, the informativeness of a node is, intuitively, the average amount of information known about the class of the input sample, given the binary activation of the node. This figure shows the average loss for one of the network architectures. Notice the logarithmic scale on the x-axis. Also notice the point at which the loss starts decreasing. This figure shows the activation fraction for the same architecture averaged across the nodes in each layer. Several things are important to note. Firstly, notice that the point at which the loss started to decrease coincides with the peak in the activation fraction. Also note that sample sets grow early in the training process, after which they shrink for the rest of the training process. Finally, the sample sets of nodes in the first layer shrink more rapidly than sample sets of nodes in deeper layers. This figure shows the predictability for the same architecture averaged across nodes in each layer. As a reminder, the predictability is proportional to the average amount of information known about a binary node activation, given the class of the input sample. This figure shows how nodes, especially those in deeper layers, become more sensitive to class membership as training progresses. Nodes in deeper layers also tend to be more sensitive to class membership. This final figure shows the informativeness for this architecture averaged across nodes in each layer. As a reminder, the informativeness is proportional to the average amount of information known about the class of the input sample given a binary node activation. The dashed line indicates the maximum informativeness that can be achieved by a node. This limit is imposed by the binary nature of the activations that we consider. The figure shows how nodes become more indicative of class membership as training progresses. However, the binary activation of any single node remains a poor predictor of class membership. In light of the sample set formation process presented earlier, we can speculatively interpret our results as follows. Initially, weight vectors are random and the magnitude of the network loss is large. Since the loss is large, samples are easily added to sample sets, and most sample sets grow. Sample sets continue growing up to the point where the loss starts to decrease. As the loss starts decreasing, nodes become more specialized and focus on specific subtasks. It is during this phase that sample sets shrink. This continues until training converges. During training, samples with zero loss do not contribute to weight updates, and therefore, sample set changes are driven by samples with non-zero loss. This interpretation views the training process as finding clusters of samples that cause coherent network behavior. The training process then models these clusters together. In conclusion, we motivate the importance of sample sets as an analysis tool by reviewing the conditions that govern the changes to these sets. We then demonstrate that the evolution of sample sets for our training is consistent across several networks. Finally, we interpret our experimental results in terms of a clustering process using the conditions that drive sample set changes. Thank you. Are there any questions?